So we're going to start off talking about Newton's first law. Now I'm going to say one thing. This is inertia. This is a law of inertia, that things tend to stay at rest when they're at rest unless an external force acts on them. Things that are in motion tend to stay in motion unless a force acts on them. I, for the life of me, can't keep straight which is the first, which is the second, which is the third. So I'm not a big stickler for expecting you to memorize which is the first and which is the second and which is the third. What I expect you to do is know how to use them. And, know that, know what inertia is. Know how it works in the world. So Newton came up with these circa 17-something. And nothing has really changed in terms of Newtonian physics. This is not something where we have groundbreaking new stuff, which is good. Things continue to move the way they did 300 years ago. That's helpful. What the first law says, what inertia says, is that if there's no net external force on something, it's not accelerating. When an object is at rest, it remains that way, and when it's in motion, it remains in motion. This is important with constant velocity, unless it experiences a net external force, a net force outside of it. Do you know the difference between net and gross? How many people here are going to pay a check? Okay. Yay! Is that a yes? I think I get a paycheck? I'm not sure.
I get a paycheck, but I'll look at it.
Okay, you should look at it sometime. Do you know the difference between your net pay and your gross pay?
One of them is before taxes.
One is before taxes, one is after taxes. So the gross force, and we don't use the term gross in physics, but it's a useful metaphor. The sort of gross forces on an object are all the forces that are acting on an object at any time. But then we start subtracting things out because things start to cancel out. So I'm sitting here, there are forces acting on my body, but I'm not accelerating. There are gross forces. The net force on me is 0 because everything cancels out as long as I'm just sitting here. That's really what net force is, and we're going to spend a lot of time calculating net force. So really what we're doing is summing up vectors. You have many forces acting on most objects at all times, and the sum of the vector forces is the net force. So it's the same methods that you used for doing non-perpendicular vectors. It's exactly the same method, which means it's exactly the same thing where I said the math isn't complicated, but the bookkeeping is tedious. It's something that rewards anal retentiveness and color coding, which for some of you was like, woohoo, give me the pencils, and for some of you, has you wanted to crawl under the desk. Same exact method, though. So we're actually going to walk through 4A practice, sample problem 4A together, and this is on page 132 in your book. And this is just summing up forces. To set up any one of these net force problems, you want to draw a free body diagram to start with. That's the best way to start these, because it gives you the visual of where the forces are. So somebody leaves their physics books on top of a drafting table inclined at a 35-degree angle. They give you a free body diagram. I'm going to make you draw your own. Find the net external force acting on the book and determine whether the book will remain at rest in this position. Remember, if net external force is not equal to 0, it's moving on whatever axis that occurs on. They've given you the free body diagram partly because you haven't learned about all these forces yet. I really like this particular textbook. The one thing I don't like is how they introduce a couple of the forces, so there will be a couple points where I interject things that come up later in the chapter, but I feel like you need to know them now. So we have a force of friction, which you know that friction exists. We haven't talked about it yet. We will a lot later. You have what they call the force of the table on the book. All surfaces exert a force on an object. If that object's being pulled down, and if you took away the table it would fall, then that table is exerting a force upward on the object. And you have the force of gravity. And like I said, they haven't given you the means to resolve this yet, but that's what we're going to do. We will end up doing a lot of these slope problems because they're really good force problems. So I'm going to shrink this down a little bit. Well, actually, no, I'm just going to center it. That's what I'm going to do. So we have to choose a coordinate system. And, I've said that we superimpose the Cartesian coordinate system on the world, and that's just great. We're accustomed to it. And we're accustomed to the Cartesian coordinate system looking like that. But the fact is, we are perfectly within our rights to do something like that and to tilt it. And when we're dealing with sloped surfaces, that is most commonly what we actually do. Reason being, on sloped surfaces, gravity don't line up. So gravity's one force. If you slope the axis, you have to resolve gravity. If you don't slope the axis, you have to resolve two other forces. So we'll get to those problems. For right now, I'm gonna superimpose that, and I can now see how badly my force vector for force on table is not at all perpendicular, but that's okay. I'll fix it. Okay, so with the axis tilted, we can see that two forces line up, and they are completely on an axis. The only one that's sort of a pain is the force of gravity. We're going to introduce a notation here. This symbol is sigma. It's a Greek letter, and it means sum of. So we're going to start to, and I think we did this with non-perpendicular vectors in chapter 3, correct? We did sum of x, sum of y. No, we did x total, y total. So we're going to start to talk about the sum of forces on the x and the sum of forces on the y. And really what that's giving us is the same information as our delta x total, delta y total. But we can use a Greek letter, and why not? And you can make a cool t-shirt that says something like, "Get some!" Except only geeks will get it. I will find it hilarious. Okay, so we're going to find our forces on the x and y axis. Well, here's the thing we got to do. I'm going to pick yet another color for a line. I'm going to do blue. I apologize in advance if I have anybody in here who's colorblind. I do rely heavily on color coding for this. Well, I know that there are two components to my force of gravity. And I'm going to name them appropriately. I'm going to name them F of G, Y, and F of G, X. Okay? And that's going to be where I have to do vector resolution. But right now, in the most generic terms possible, I want to think about what this sum of forces on the x-axis is. Name me a force on the x-axis that you can see. Force friction. Okay. So we have force of friction, and that's going this direction. We have, what else? What else have we? We have force of gravity on the x, F of gx. Just go in that direction. Okay. Well, now we're just going to leave that alone. We know that. What about our force on the y-axis?
Force the table.
We got force of table, up. What else? Force of gravity on the y. And I'm gonna do something here because we know that both forces of gravity are working downwards. I'm going to make these something that we're subtracting. Okay. Now this does violate our standard Cartesian coordinate system because force of gravity on the x, the way this is drawn, is in the first quadrant. That's why I would have drawn it the other way, but I'm going with what I was given in this case. So force of gravity on the x, force of gravity on the y are both working to pull this object down the slope and down towards the center of the earth. Okay, well I'm given the magnitude, oh, I need to put my little arrow in there. I'm given the magnitude for force of friction, I'm given the magnitude of force of table on the book, and I can find the force of gravity using some geometry and some trig. We were told that this angle is 35 degrees. Oh, this is the part I hate. So, we need to know what this angle is. There is a beautiful, easy, simple way to prove that that angle is 35 degrees, because I can tell you it is. Let me see if I can do it cold. Buckle your seatbelts, folks. We've got some analytical geometry coming here. So I've pulled this out from the problem just to prove that that angle is the same as this angle, to prove that that theta, whoops, is equal to this theta. So those two angles are both part of a 90-degree triangle. Can we accept that? Which means that this angle and this entire angle add up to 180, correct? Okay. Now I'm going to draw in a different color. I want you to look at this triangle. Well, that's where our little red angle theta exists. This angle and this angle and this angle add up to 90 because they're the internal angles of a triangle. Okay. All right, so we can also accept, I hope, that this angle and this angle and this angle add up to 90. Good God, that's a lot of 90s. Can we accept that this angle, okay, this is 90. Okay, so let's back it up. We've got, and I put some made-up numbers in there. These three form an angle, and this whole thing here is a 90. So we've got 30, 60, 90. If we go ahead and look at our line here, and we make another triangle using that, this is still 60. This has not changed. Now this is 90. What must this angle be? 30. This angle is always going to be the same as the angle at which the surface is inclined. Okay? So that's not the most elegant proof of it I've ever done. I went around the barn a couple times, sorry. But anyway, you know, the other option is you just blindly accept that the angle between gravity and the sloped surface is the same as the angle between the horizon and the sloped surface. But I think it's nicer if you can prove it geometrically. Okay, so with all that out of the way, let's get that junk gone. We know that this angle theta is 35 degrees. Can you write an expression, whoops, can you write an expression now for your f of g on the x or y? So sum of forces x equals force of friction minus the force of gravity times what? So this is on the x, here's your angle, it's directly opposite. Sine. Times sine theta, which is 35. Sum of forces on the y equals force of the table minus, what's your expression for your force of gravity on the y? F of g times cosine theta. All right. Okay, I've got a raw answer of force on the x being 11 newtons minus 12.6186816, etc. What does that give you? Sum of forces on the x is equal to negative 1.618 blah blah blah. We got 2 sig figs, so it's going to be 1.6. Is there a net force on the x-axis? Yeah. In what direction is it acting? Down the table. The book is going to slide down the table on the x-axis. Now, I probably should have done the y-axis first because I want to ask you a really obvious question. Does the problem mention that the book is spontaneously rising into the air or crashing through the surface of the drafting table? It does not. So what would you then assume might be the net force on the y-axis? If it ain't moving, what's the net force? 0. It's at equilibrium on the y-axis. Let's prove that to ourselves, because you don't know that yet, technically. I'm sort of foreshadowing that. Sum of forces on the y is equal to 18 newtons minus quantity, 22 newtons times cosine 35. What do you get? Okay, so according to this, and we'll talk about the precision involved in this, you have a tiny little bit of gravity winning here. We know gravity isn't winning because it's not crashing through the table. So when you get to your 2 sig figs, because this gives you, oh, that's ugly. Oh, that's so hideous. That is so hideous. They did such a terrible job on rounding. Force on the y-axis is 0. We know this. With their terrible sig figs and their problem setup, you get negative 0.02134, blah, blah, blah. And if we actually faithfully follow the rules for sig figs, you get a force of negative 0.021. But it's not crashing through the table. They did a bad job of giving you the force of gravity. The force of gravity needs a few more sig figs. In a problem like this, you would, so, again, we're going to disregard their bad sig figs. In a problem like this, you would say that the net force on the object is negative 1.6, well, it would just be 1.6, huh? Newtons. And you could say down slope, because remember this is a vector. You could say down slope, yes, sir. No, he's in study hall right now. Oh, wait. Can somebody run after him? I will pass out. Oh, okay. Don't beat him up yet. Are you doing grades right now?
Yeah.
Okay. Don't beat him up. Come here.
Sponsor your class then.
Oh, okay, good. Then do whatever you need to.
Because I know that he.
Well, come on. Yeah, that's true. They pretty much all failed chapter 6. They're doing retests tomorrow.
Yeah, I'm worried about.
It was a cluster.
He's gonna see him.
Oh, okay. Okay, never mind. I was going to say, don't go club the poor kid.
That's what I'm. 17.
We should have a conversation at lunch.
Okay.
Okay. So, what you would typically say is that the net force is negative 1.6 newtons down the slope. You could say negative 1.6 newtons. Oh my God, I was recording all of that, wasn't I? You could also say negative 1.6 newtons towards the positive x, towards quadrant 1. You could say, you could specify a lot of things. You can't say north, south, east, or west. We don't have them. You cannot just say down. What does down imply? Straight, yeah, through the table. You can't say that. It's not going straight down. It's going down the slope. Question. Yeah. Are you, yes. Okay. It's a good question. It's a good conversation to have. Sign can stand in as a proxy for direction. We just talked about proxies in chemistry this morning. When you say it's got a negative, when you say it's got a negative force on it, it implies down. Most often we think about it, in the negative, on the negative axis or negative y or negative x axis. Here, the magnitude of the force, so if we just think about that, the magnitude of the force is 1.6 newtons. The force is down slope. Is it redundant to say it's a negative force down slope? Yeah, actually it might be. An argument could be made. Let me consider that. That's going to become more important in section 4 of this chapter, where we're dealing a lot with frictional forces. And you don't know why yet, but I'm going to go ahead and foreshadow that one too. Frictional forces always oppose motion. But sometimes they're in a positive direction. It depends on the motion. Magnitude of the force is 1.6 newtons down slope. And, the The book just, actually your book just, they don't even give a direction. They don't give, yeah, they say it's a 2 Newton positive force because that's positive x-axis. I think that's somewhat disingenuous, but we'll talk more about that. At this point, what I'm going to say is, you can guess what this is. The 4A problems, number 1 through 4, page 133. And I'm going to turn on your Pandora station and give you 18 minutes to start acclimating yourself to these. Tomorrow we're going to check in on them and probably do some additional practice. I'll probably have worksheets for you. Tuesday, because we are off on Monday. Do you realize we have 2 4-day weeks right on the heels of one another? It's a wonderful thing. So Tuesday you'll have a FIP quiz on net forces and free bodies. I expect you to draw a free body diagram with every single one of these. If you want colored pencils, I have them. That's it.